in order to understand how and why energy is released in nuclear fission, we are looking at an example that I just make up, but it kind of explains and we should then be able to understand why this generates energy. We are going to pretend it's something that is not really happening, but still it makes it easier to understand what is going on and why and where the energy comes from. So we have learned already that the nuclear fission means that a heavy nucleus is split up into two lighter nuclei. So we just take an example and could be something else. But when I'm looking at this graphics here, I see the uranium-235, which is certainly a good example. So what we do to have an energy balance is we look at the energy before and after. And this is something we've done before in mechanics, for example. The potential energy is converted into or potential into kinetic energy. So we look at the beginning, at the end, it must be the same. So here it's a little bit different, but we will see that later. So what we do, and this is totally different to reality, but when we look at the energy, we pretend that if we take, for example, this uranium-235 nucleus, we see what do we have to do in order to separate all nucleons from this nucleus. And what we need to do is we need to bring up all the binding energy, because we need to pull them apart, so work against the strong forces. And what we see in this diagram is a bonding energy or binding energy of about 7.6 mega electron volts per nucleon. So this is kind of the activation energy we need. This is the energy that we have that is already in the nucleus, and so this is 235 nucleons times 7.6 mega electron volt per nucleon, and this is 1786 mega electron volts. So with this energy we can separate all nucleons, and then we don't have this nucleus anymore. But what happens in this nuclear reaction is that we end up having two lighter nuclei. So this could be, for example, this one here with a mass of 119. So so now we look at the second step, and the product of this reaction are two nuclei. So the energy that they have could be, for example, 119, and what do we have here? Let's say it's 8.5 mega electron volts, and then we have 235 minus 119. That leaves us with another 116 nucleons, and this is a bit more on the left side, so it's even higher. So let's say it's 8.55 mega electron volts. It's not very precisely, but we get an idea of how this works. So this would be 2003 mega electron volts. And since this is a negative bonding energy, meaning that it is being released when the single nucleons are put together to these two medium heavy nuclei. And we can calculate this energy. So this is E2 minus E1, and that leaves us with 217 mega electron volts. And now again, where does this energy come from? We have learned before that delta E is equal to delta M, the mass defect, times C squared. So let me explain this again. In the first step, we put energy into the system, and this generates some mass. We've seen before that the single nucleons are heavier than when they are put together in a nucleus. So here we transform energy into mass, and then we go over here, and in the second step we out of these 235 nucleons we form two other nuclei with a different energy. So when they are put together, again, we lose some mass because the products are lighter than and have less mass than the single nucleons, and this mass defect is converted into energy according to the formula E is equal to mc squared. Now, a bit later we will learn how this works in reality. So, because this would be just too much of energy, it would be impossible to pull them apart like this. But all we did here was comparing the two states of energy, calculating the difference, and hopefully understanding how energy is released and where it comes from.